Hello, my name is Jared Skeens and welcome to the Zoom room. Today we want to look at mechanics, friction and inclined planes, part 2, net force. Now in part 1 we looked at equilibrium and we looked at Newton's first law. And Newton's first law says that an object that is at rest or in constant velocity will remain so unless it is acted upon by an outside force. And we talked about the fact that it doesn't mean there's only one force acting on it. There are many forces acting on a particular object at any given moment. What we're really talking about is the net force, or the total of all the forces together. If the total of all the forces together are balanced, that is, your horizontal forces are balanced and your vertical forces are balanced, then the object will remain at rest or will remain at a constant velocity. So in part 1, we dealt with those systems that were in equilibrium. Now in part 2, we're going to look at what happens when our net force actually has a resultant, or we call that resultant force the net force, the force that is the result of all of those forces put together. So just to remind us, we've been adding layers to our mechanics understanding. Our problems are becoming cumulative. So in addition to the distance, velocity, acceleration formulas, and addition into the skill of resolving forces, we added friction, which is the coefficient of friction times the normal contact force. We also looked very briefly at the force due to gravity, which is just mass times gravity, which basically gives us, leads us then to Newton's second law. And Newton's second law is what gives us this concept for a net force. And that is that force is equal to mass times acceleration. Newton's second law is force equals to mass times acceleration. So when we combine that with our understanding of net force being the sum of all forces acting on a particular object, we now have an ability to create an equation. And you'll see how that works out in the example problems. I have also listed here the Suvat formulas so that it's a little bit easier to bring those to mind when we need them. So let's get started. Let's look at the first problem here that we're going to attack today. And it says a particle of mass 18 kilograms is on a plane inclined at an angle of 30 degrees to the horizontal. The particle is projected up a line of greatest slope of the plane with a speed of 20 meters per second. Now we're just going to do part 2 because part 1 has to do with a part of the mechanics book that we haven't gotten to yet. So part 2, given instead that the plane is rough and the coefficient of friction between the particle and the plane is 0.25, find the speed of the particle as it returns to its starting point. Notice that it's 8 points, so we're jumping right into a multi-step problem. Like I said, as you continue down the mechanics book, the problems tend to get cumulative. So let's go to the board, see what we got here. Remember, first things first, establish if your system is in equilibrium or not. So this one, we see that this is not going to be a constant velocity because this object is being propelled at 20 meters per second, and it's going to go up to a point and then it's going to come back, and we have to find the speed when it returns. So that's not at rest or constant velocity. So that means we have a net force acting here, okay? And it also means that we have a force equals mass times acceleration. This is our net force that we're going to work with. So that was our first question. Is it in equilibrium or not? And this one is not. Second question has to do with friction. So this is also about friction in inclined planes. Do we have friction? And it said that the plane is rough. So we have rough, and the coefficient of friction is given to us 0.25. So we need to watch the friction. So we draw our inclined plane. You need a good diagram with some space to work. So we have an inclined plane at 30 degrees. Our object is being propelled upwards or up the plane at 20 meters per second. And so if it's going up the plane, that means the friction is resisting that motion. So the friction is going to be going down the plane. And this object is going to reach a point P, which is going to stop, and then it's going to come back, and we need to find the speed that it reaches at the bottom, okay? So the first thing that we're going to want to do, we've got friction here, so we need to find the normal contact force, and we need to also resolve our force of gravity because we're on an inclined plane. So here is our gravity is going to pull straight down, and this is 18 mass times gravity, 18 times 10, so this is 180 newtons, but this is not perpendicular to our plane. We want all of our forces parallel and perpendicular to the plane. So we're going to take this one and we're going to make it perpendicular, and we're going to make one also parallel to the plane. So remember that your angle in the inclined plane is also the angle in your triangle that you're resolving with respect to gravity there. So what we want to do is we want to take 180 sine of 30 degrees. So we have a 90-degree force, or 90 Newton force that's acting parallel down the plane. And if we do 180 cosine of 30 degrees, we get 155.88 Newton that is acting downwards. And because there's no other vertical forces, when I say vertical, I actually mean perpendicular, vertical in the sense of the object, or actually perpendicular to the plane. We don't have any of those kind of forces. So that means this is also the normal contact force that is from the plane pushing back up against the object. So we now have these, so we can calculate the friction. So our force of friction is going to be the 0.25 times our normal contact force, 155.88, and that is going to give us 38.97. So there's our force of friction, 38.97. And we have our force resolved from gravity going down parallel the slope. And we have our normal contact force, and we have our velocity. So now what we want to do is we want to create an equation to find the force that's going up the hill here, okay? Now the reason why we want to find the force going up the hill here is because we want to find acceleration. And acceleration is an important part of determining velocity. So remember, what we're trying to solve is the velocity of this object when it gets back down the hill. So we now, because we know net force is basically the same thing as mass times acceleration, we now can create an equation from this. So mass is 18, A, we don't know the acceleration, equals, and it's the net force. So that means the 90 coming down, which I'm going to make negative because it's working against our direction. The 90, the gravity is working against our motion forward. So negative 90, and also a negative 38.97 is equal to mass times acceleration. So what we're doing is we're combining resultant force with Newton's second law into an equation. So when we get this, we get 18A equals, and so we have a negative 128.97, and then that means that A equals a negative 7.165. So here is our acceleration, a negative 7, which is what we want. It's negative acceleration means deceleration. So this is slowing down as it goes up the hill. And we know that eventually this 20 meters per second is going to turn into a 0, at which point it's going to stop and then it's going to come back. So now that we have our acceleration, now what we need to do is we need to calculate the distance that this has traveled. Because if you notice over here, distance, we already have initial velocity and final velocity. We have acceleration going up, but we also need to know the distance that it has traveled. So we can figure out the distance through the formula v squared equals u squared plus 2as. Notice we have initial velocity, final velocity, and acceleration, so we can find the distance. So our v squared is going to be the 0 squared. That's the final distance when it comes to a stop. Initial velocity is 20 squared plus 2 times a. We just calculated a. And s as the distance. Okay, so when we solve for distance, our distance is going to come out to here 27.91 meters. You can do the calculation and find that distance from here to here is 27.91 meters. So now we know how far it has traveled up. Now what we need to do is this box now has stopped, or this object has stopped. It's now going to start sliding back down the slope and it's going to gain speed, and we need to find the speed at the bottom. So we need to recalculate the acceleration. Before, the acceleration was a deceleration, it's slowing down. Now it's going to start sliding and gaining speed, so we need to recalculate the acceleration, and our friction has changed directions. Now that the box is sliding down, the plane is resisting the motion and our friction is acting up the plane. So we need to redo our calculation. We still have 18A, but now our resultant forces are mixed up a little bit. We still have the 90 going down. This time I'm going to make it positive because it is now in the same direction as our motion. And the force due to gravity, or sorry, the force from our friction is still going to be negative because it's resisting our motion. So minus our 38.97. So we get 18A equals, so 90 minus that, 51.03. then divided by 18 gives us 2.835. So acceleration 2.835. And notice it's positive because it's now going in the direction of our motion. Our motion is going downhill and our acceleration is making it speed up in that same direction. So here's our new acceleration. Now we don't want to find distance, but we want to find final velocity. We can still use this same equation again, this velocity, because we have initial velocity and we have acceleration, and now we have distance, so we can use that to find the final velocity. So our v squared equals u squared. Now our original is 0 plus 2a is now 2.835 times the distance is 27.91. So make sure you look carefully through your Suvat equations for the one that has the information that you've already worked out, and also has the variable of which one you're looking for. So when we get this, 2 times 2.835 times 27.91 is equal to 158. So v squared equals 158.25. Then don't forget to square root, because this is a square. So square root our answer, and we get 12.57, or v equals 12.6 meters per second. And that's to 3 significant figures. And there's our answer to the speed of what this box will reach when it gets back to the starting point. So here's our first question. Again, really quickly, those first things you need to ask yourself. One is the system in equilibrium, or does it have a net force acting on that? You tell that by whether it is either at rest or constant velocity means equilibrium, and if it's in motion or not constant velocity, basically not constant motion, then you have a resultant force acting on it. If you have any kind of acceleration at all, then you have a net force. If you don't have acceleration, if your acceleration is 0, it's in equilibrium. That's the first thing you establish. Second of all, you look for whether or not you have to calculate friction, smooth or rough. Third thing, you need to resolve your forces. So make sure you have a good diagram with space on it so that you can see what you're doing. Resolve those forces parallel and perpendicular to your object, to the plane. And then now we've added on the concept of if there's a net force, you can create an equation, because mass times acceleration is equal to your resultant force that we're now calling the net force. Okay, so let's set up another problem. Okay, let's get into our second question here. And let's go to the screen so we can read it. It says a block of mass 3 kilograms is initially at rest on a rough horizontal plane. A force of magnitude 6 newtons is applied to the block at an angle of theta above the horizontal, where cosine theta equals 24/25. The force is applied for a period of 5 seconds, during which time the block moves a distance of 4.5 meters. That's a lot of information. So before we get into the question, let's just go back and look at our diagram. We need to make it, because the problem does not provide the diagram. So that means we need to draw a good diagram. So here we have a horizontal surface. It says that the mass is 3 kilograms. It says that the surface is rough, which means that we're going to have friction resisting our motion. We see that the object starts at rest, so that's 0 velocity. We see that there's a 6 Newton force acting at an angle of theta degrees to the horizontal. So you just make your little, from that corner, you just make your parallel to the horizon and go up theta degrees. We see that this object traveled 4.5 meters in 5 seconds. So I put that information down here. We see that this angle also has a value where cosine of the angle is equal to 24/25. So what I did is I just did Pythagorean theorem really quick, and because the 25 would be the hypotenuse and the 24 would be the adjacent side. So 25 squared minus 24 squared is 49. Square root of that is 7. So that means sine of theta, which is opposite over hypotenuse, would be 7/25. So this is the information that we're dealing with. There's kind of a lot of information there. Now let's look at the question. So the question says, find the magnitude of the friction force on the block. So notice we're finding the entire value of the friction, not just the coefficient of friction. So let's work with that question first before we get to the other parts. Now, one of the things that we need is we need to find acceleration, okay? Because this friction force is going to be in the net force formula, okay? So if we look at it, our net force, which is mass times acceleration, equals the force going forward, that's going to be this one here, minus the force going backward. So the force going forward is going to be 6 cosine of theta, which is 24/25, minus our force of friction. I'll just put it as force of friction here. So notice we have 2 unknowns. So what we need to do first is we need to find our acceleration so that we can solve for this force of friction. So to find the acceleration, let's look at this, because we can't use this formula. So if you're not using your net force formula, then we want to go to suva. And the information that we're provided is distance and time. So when we look at distance and time, and we have an initial velocity, we have distance, and we have time. So we can use this formula down here at the bottom, and we get distance 4.5 equals ut 0 times 5, because we started out initial velocity of 0, plus 1/2 at squared. So a is the acceleration is the only variable there. So we have 4.5 equals, this is 25 halves, so 25 halves is 12.5 a. So a then equals 4.5 divided by 12.5 equals 0.36. So our acceleration is 0.36. That is not a final answer, but that's a step in the direction that we need. Now we can put that over here and do 3 times 0.36. Multiply that by 3, and we get 1.08. 1.08 equals, we can calculate this, 6 times our 24/25 is 5.76 minus our force due to friction. So if we just move that to the other side, our force due to friction is equal to 5.76 minus the 1.08, which equals minus 1.08, 4.68. So our force due to friction is 4.68 newtons. So that is our final answer for part I. Okay, so we set up our formula. We have two unknowns. So we go to our SUBOT with the information provided to help us find acceleration. Then we're able to find the force due to friction. Now let's go and look at the second part of the question. And the second part of the question says, show that the coefficient of friction between the block and the plane is 0.165 correct to 3 significant figures. So in order to find the coefficient of friction, we need to, so now we're going to work on part II, and friction of 4.68 is equal to mu times the normal contact force. So we calculated friction as a whole. Now we want to find the parts. We're asked to show that mu is 0.165, and we need to find normal contact force. So to do that, let's look at our gravity here. So our gravity is pulling down 3 times 10 at 30 newtons. So, but remember, normal contact force is not always just resolving gravity. You have to look at, are there any other vertical forces acting here? And there's another vertical force that is actually pulling up over here. See, this 6 newtons is pulling in the up direction. So not all 30 newtons of the gravity is acting on this object. You have 30 newtons here, but you have some going the other direction. So that's going to reduce the normal contact force right here. So the normal contact force is basically like your resultant of the vertical forces. So our normal contact force is equal to the 30 minus, because it's working against the gravity, 6 sine, because this is the opposite, which is our 7/25, which equals, for our normal contact force, 30 minus 6 times 7/25, and we get 28.32. That's the normal contact force. So now we have 4.68 equals 28.32 mu. So our mu equals 4.68 divided by this one here, and we get 0.1652. 0.1652. So we need to show that it rounds to 0.165. There is our coefficient of friction, and we were able to show it. But the key here is to remember your normal contact force is the net force of perpendicular forces acting on your object. Many students just assume that it's the gravity force only, but it's not. It's the net force of all the perpendicular forces acting on it. So don't forget that. Okay, let's go back and look at the third question. I believe there's a third one here. It says, when the block has moved a distance of 4.5 meters, the force of magnitude 6 newtons is removed, and the block then decelerates to rest. Find the total time for which the block is in motion. And this is worth 4 points. Okay, so now our block has come over here and it has reached this 4.5 meter mark. The 6 newtons is now removed, and we're going to continue on here. until the block comes to rest. We want to come over here to where the velocity is 0. And there is still friction acting, but our friction is now different because the normal contact force is now different. We've removed this vertical part here, so that's going to change the normal contact force, which is going to change the friction. So every time you have a change in your system, you need to follow it all the way through to see how it affects everything else. So we want to find the total time that it takes to get to rest. So we already have our first time here, T1 is 5 seconds. Now we want to find T2 over here, okay? So to do that, let's first find what is our velocity at this point. It started at 0. What is our velocity right here? Okay, so to find that, we have the distance, we have acceleration, and we have initial velocity. So we want to do a part 3. Let's find out our starting velocity. So, or the final velocity for this segment. So v squared equals 0 squared plus 2 times acceleration. The acceleration for this part was 0.36. Now this acceleration will be different. This will actually be a deceleration. So we'll need to calculate that again. So we have 0.36, and the distance that it traveled is 4.5. So our velocity equals 2 times 0.36 times 4.5, and you're going to see that the velocity comes out to 1.8. I'll let you do the calculations. V equals 1.8 meters per second. So now we have 1.8 here. And we want to find now our deceleration. So to find our deceleration, we can use this formula up here, but we need to recalculate our friction though. Our friction needs to have a different value here. So we can calculate our acceleration from here. You might also even be able to calculate your acceleration from one of these other places as well. But we don't have the distance and we don't have the time. So notice we're missing the time, we're missing the distance. So we're going to use our net force formula. So our 3A, it still has the same mass, equals, we've lost this force, so the only force acting on it horizontally is our force of friction. So our 3A equals our, I'm going to put negative because it's working against us. We already figured out the coefficient of friction, which, by the way, that will stay the same because that has to do with the surface. So the surface hasn't changed, it's the normal contact force that changed. So a negative 0.165, now it's just the 30 is the normal contact force because the 6 newtons was taken away, so times 30, and we get A equals a negative 1.65. Negative 1.65 meters per second squared. Notice it's deceleration, so that's a good sign there. We have our deceleration. Now we need to figure out time. So we have starting velocity, final velocity, and we have acceleration. We want to find time, so we can use this one up here because we have all the other 3. So our final velocity for this segment is going to be the 0. So make sure when you're looking at velocity with different segments, you get your initial and starting correct. So now we want the final velocity to be 0. Our initial velocity is 1.8. Our acceleration is a negative 1.65 times t. So that means 1.65 t equals 1.8, which means t equals, and this is our t2 by the way, because it's asking for total time. So our t2 is 1.8 divided by 1.65, which is 1.09. 1.09 seconds. So our total time is equal to 5. That's the 5 seconds it took to get from here to here, plus the 1.09 equals, and I hope that you can see that. Let me move that down. 6.09 seconds, just barely got it in there. So 6.09 seconds, and that is the total amount of time that it took for the object to get from the starting point until it rested at, come to rest at the end. Okay, so that one had several different parts to it. Notice that we kind of went back and forth between our formula that deals with net force, Newton's second law, mass times acceleration, and the Suvat formulas. So things are a little bit blended together, and you gotta look at the information that you have and what information you need to find. So let me set up one more question and hope that this helps develop your thinking. Your mental approach and what you're looking for is half the battle, and then the skill in executing it is the other half. Okay, here is our last question for this video, and let's get right to it. It says a particle is projected from a point P with initial speed u meters per second up a line of greatest slope PQR of a rough inclined plane. The distances P to Q and Q to R are both equal to 0.8 meters. The particle takes 0.6 seconds to travel from P to Q and 1 second to travel from Q to R. Show that the deceleration of the particle is 2/3 meter per second squared, and hence find u, giving your answer as an exact fraction. So let's just look at our diagram real quick and think through our mental questions that we need to ask. First one, is it in equilibrium or does it have a net force? Well, this has a net force. Why? Because it is not rest, nor is it going in constant motion. And it already mentioned to find the deceleration. So if you have any kind of acceleration, then you are in a net force situation, not in equilibrium. Second thing is, it says that it is rough, meaning we need to have a friction force involved. And of course, friction is going to go against our motion. It says our initial velocity is u. It says that the distance between these objects are 0.8 for each segment here, P to Q and Q to R. It takes 0.6 seconds to go the first section and 1 second to go the second section of it. So we have to find, notice it does not give mass. It does not give the angle here. It does not give acceleration. So there are a lot of things that we do not have. It does ask us to find two things, deceleration and this initial velocity. So since we're looking for two things, probably a system of equations. And it's not going to be helpful to use our net force at this point because we are missing the angle, which means we can't resolve our gravity here. We're missing the mass. So we would have a very incomplete formula if we tried to use net force, which means we should probably look at suva. So what we want to look at is something that has distance and time and also has our two missing variables of initial velocity and acceleration. So when we look at that, here we have, we want distance and time. We want distance and time and has our two missing variables. So this equation down here is probably the equation that we want to use. So let's set up our equation. So one distance is 0.8. Distance equals u times t. Time is 0.6. So 0.6 u plus 1/2 a t squared. So 0.6 squared. And then our second equation will be taking the total distance, because if we only take this top part, we don't have our initial velocity at this point. So our initial velocity is down here. So we want to take this whole segment. So 0.8 and 0.8 is 1.6. And the whole time is 1.6 u plus 1/2 a and 1.6 squared. So don't try to just take that final segment, because you'll start mixing up your initial velocity in two different places. You don't want that. You want one initial velocity from the starting point. So do this first segment and then do the total segment. Now we need to clean this up a little bit. So our 0.6 squared is 0.36. And so since that is, and 0.36 divided by 2 is 0.18. So all of this is 0.18. It has 2 decimals to it. I don't like to work with decimals. I'm going to move the decimals over twice. So that means this becomes 80, 1, 2, equals 60 u, and then plus 8, move over twice, becomes 18a. Okay, and then this one down here, we need to take 1.6 squared, 1.6 squared, divide it by 2 is 1.28. So we're going to make that 128a. And then this becomes, moves over twice, 160 u, and move this over twice, 160. So we can probably clean this up a little bit. And if we change this, we can divide this top one by 2. Divide this top one by 2 gives us 40 equals 30 u plus 9a, dividing that one by 2. And if we, let's see here, how else can we reduce this? We can also divide this one by 16. We divide this one by 16, that would give 10, and 10. We divide 128 by 16, gives 8. So now we want the 10 and the 30 here to match up. So we're going to we divided by 16, but now we're going to multiply by 3. So just playing with the numbers to get it. You can do substitution if you want. I like elimination, so I prefer to kind of play with the numbers. So I divided everything by 16. Now I'm multiplying it by 3. So that gives 30 equals 30u plus 24a. And we're going to subtract going up. So that gives a negative 10 equals 24 minus 9. 24 minus 9 is 15. A, divide by 15, A equals a negative 10 fifteenths, which then equals a negative 2/3 meters per second squared. Now it said show that the deceleration is 2/3. So by finding that the acceleration is a negative 2/3 meters per second squared, the negative is the same thing as saying deceleration. So a negative acceleration is deceleration. So we found that part. Now we need to find the u. So we can come right back up into, say, this one here. So 10 equals 10u plus 8 times a negative 2/3. 10u equals, and when we do this, we get 8 times negative 2/3 is that one. It'll be negative, so we need to add it to 10 is 46/3, which equals 15.3. And then we divide that by 10, and we're just going to see, oh, but it wants exact. So that was 40/3. Said find the exact as a fraction. 40, what was that? As a fraction again? 46/3. So divide by 10, that would be 46/30. And 46/30 reduces to 23/15 meters per second. So I forgot it said to make u as an exact fraction. So don't change it to decimals. So we found our a and our u using simultaneous equations. Takes a little bit of time, and that's probably why it was worth the extra points. Now let's go look at the second part of the question here. Second part of the question says, given that the plane is inclined at 3 degrees, so now I'm going to put in 3 degrees here into our angle, find the value of the coefficient of friction between the particle and the plane. So I'm going to erase some of this so that we have some space. Okay, I erased the previous work. I did keep the acceleration, but I erased it so that we have room to work. What we want to find now is our friction here. So the coefficient of friction, the mu. So we're going to go back to our net force now because we don't need the suva anymore. And we are given a 3 degrees. So now we can partially resolve the forces of this. So if this is straight down, we don't know the mass. So we're just going to have to use the letter m times 10. So this is 10 m newtons going straight down. And we want to resolve it perpendicularly and horizontally with or parallel to our plane. So this one coming down is going to be 10 m sine of 3 degrees. And this one over here is our 10 m cosine of 3 degrees. Okay, so let's put together our net force formula. So that is mass times acceleration. So mass times acceleration is a negative 2/3 equals, and these are both going against our motion. So a negative force of friction, which is our mu, times the normal contact force, which is our 10 m cosine 3. And you know what? I think I'm going to write this down a little lower because we need to kind of have a long equation here. So our mass times acceleration, that's our force net force equals mass times acceleration up here. Net force, mass times acceleration. So the mass we don't know, acceleration is -2/3, equals our force of friction, which is mu times the normal contact force, 10m cosine 3 degrees, minus, and it's negative because it's going against this, minus the 10m sine of 3 degrees. Okay. Now, this looks a little complicated because we have two unknowns. However, one of the unknowns is on both sides of the equation. So, and we have this negative here. So what we can do is we can divide everything by a -m. We don't need to find m anyway. We're looking for mu. And the m occurs in all the parts, and there's a negative on all the parts. So we'll just divide by a -m, and that gives us 2/3 equals 10 cosine 3 degrees mu minus or plus 10 sine 3 degrees. So now we solve for mu here. We can take the 2/3 minus the 10 sine 3. That gives us 0.1433. So the 2/3 minus the 10 sine 3, because we divided out a -m, so it crossed out the negatives and the m's, equals 10 cosine 3, 10 cosine, just want to check to make sure I did that right, plus 10 sine 3. Oh, yeah. Sorry, 2/3 minus 10 sine 3. Yes, okay, got that right. And then 10 cosine 3 is of 3 degrees. 10 cosine 3 is 9.986. So our mu then, 0.1433 divided by the 9.986 equals a 0.01435. Mu equals, can you see that? Yeah, 0.01435, which means 3 significant figures. Remember, 0 is not significant when it's on the left. So 0.144 is our value for mu. And this is our second problem. So this one here is a little tricky because it's got those two unknowns, but only one equation. However, you can divide out the variable. Normally, you don't want to divide out variables. In this case, it's okay simply because you don't need that variable to solve for it. So you could have also factored it out, and then when you divide it, it would cancel. Either way, just divide by a negative, a little easier, and then solve for mu. Got some trig stuff in there. Make sure your calculator's in degree mode. So that concludes our part 2, the net force. Looked at several different types. Again, you have that net force, that cumulative formula that now you're adding that extra layer to your question with this force equals mass times acceleration. That's very important, and you will continue to use that moving forward. And we see how it blended with our suvat and with our resolving forces that we had learned in the previous units. So thank you again for joining me, and in the next unit, we'll be looking at connected particles. So hope to see you again next time.